Guys, welcome back to Basic Chemistry Plus. And like I said, guys, we had three videos so far in the polymers chapter, and this is the last video on that. So we'll be completing this chapter in this video, and then we'll be looking into some previous year question papers as well. So first thing is, today we are going to talk about the biodegradable polymers. So guys, there are many instances where they have asked questions from these biodegradable polymers. So the first polymer that I'll be talking about is PHBV. The name of this polymer is also very complicated for us to remember, which goes like poly beta hydroxybutyrate co beta hydroxyvalerate. That's the name of this polymer. But you can just remember one thing: there is butyrate and valerate in the end of it. Okay, why do I ask you to remember? If they suddenly give you the question with respect to the big name, they generally give it with respect to the shorter name, which is PHBV. But if they any which ways give you the thing with respect to the uh, big name, so that you can understand, okay, there was something called butyrate, there was something called valerate. So guys, how do you make the polymer? uh, by mistake I have written it earlier only because it was taking, not by mistake actually, it was taking a lot of time, so I thought of writing it already. So over here you can see that 3 hydroxypentanoic butanoic acid and 3 hydroxypentanoic acid. So guys, it's a very simple, two monomers are very simple over here. 3 hydroxypentanoic, this is, you can see that 1 2 3 4, 3 hydroxybutanoic acid and 1 2 3 4 5 ethyl group in there. So 3 hydroxypentanoic acid. So combining them together, what do we get it? You just have to make an ester out of it. Okay. Always remember, whenever esterification occurs, OH comes from the acid, H comes from the base. Okay. So you get the polymer look like, I'll be writing a little fast this time. CH2, C double bond E, bond O, bond CH, bond ET, bond CH2, C double bond O, and then keep on continuing with this. Okay. So this is my polymer, guys. Okay. This is PHBV. Very simple. 3 hydroxybutanoic acid and 3 hydroxypentanoic acid. By look of it, might look some difficult things in there. But guys, in reality, if you just draw it, it is not really that difficult. Okay. Then nylon 2,6. Like I told you, 2 and 6 are nothing but the number of carbons present here. So what are the molecules, guys? Glycine. You know that glycine is nothing but the simplest amino acid in there, right? And then aminocaproic acid. Aminocaproic acid is nothing but an amino acid where we have, see, 2 and 6. So in the aminocaproic acid, how many carbons should I have? 6 carbon is what I need to have. So there is a carboxylic acid, there is an NH2 because it's an amino acid. So NH2 and carboxylic acid would be there. So leaving the carboxylic acid's carbon, I would need 5 more CH2 groups. So this is what we have now. So this is aminocaproic acid. So guys, it is also going to be a polyamide. I have just drawn it over here. It is also going to be a polyamide if you just take out the water from here. So guys, that's it. That's it about all the different kind of the polymers, the different kind of biodegradable polymers are there. I guess there was, this is it. Okay, so all the major part is over, guys. Then we have a small thing which is vulcanization of rubber. This is something I told you in the very first class, that vulcanization is something that is needed to increase the durability or increase the tensile strength of the rubber, right? Over here you can see that what were the problems in the natural rubber. So natural rubber becomes soft at high temperature, so you cannot really work it as a tire, because when you are putting it as a tire, what happens is it creates a lot of energy in there, right? A lot of heat in there, so it might get spoiled. So above 335 Kelvin, it doesn't really work in there, and it is very brittle at low temperature. So guys, we can't really use it to make any hard substances or anything like that, right? The second problem which was there about the rubber, I guess it is not really visible, right? Now it is. So it is soluble in a non-polar solvent and is non-resistant to attack by oxidizing agent. That means if you make, let's say you made something with rubber. Let's say I made this watch with a rubber. All right. So if it is coming under the influence of this air, the air has a lot of oxygen in that. So what would happen is, guys, it would undergo oxidation and it would get oxidizing. Okay. So that's why we cannot really use it a normal rubber. And shows high absorption capacity of water, means it would just absorb water. So guys, you can understand that if it absorbs water, what would happen? It would be, moist, it would be soaked with water. So guys, these are the problems that we had with the natural rubber. So that's why we had to vulcanize it. Now, what is vulcanization of rubber? So over here, what we get to see is, what we do is we give some sulfur to it and then we heat it, and that's it. So what would the sulfurs do, guys? Let's say this is our natural rubber. Just look at the picture first before you read it. Okay, look at the picture. Over here, what's happening? This is the normal rubber. Okay, the rubber strands are, this is the isoprene unit, right? Isoprene unit, when they are connected in the trans format, that is called rubber, and when it is cis format, that is called gatta parcha, right? So this is our rubber unit. When the sulfurs are actually, what sulfur would do, the sulfurs would just make bonds between them like this and connect them together. Okay, so what would happen? Just like united we stand, divided we fall, like that. Dividedly, they are not really that strong, but the moment you have some sulfurs linking them like that, what would happen is they would be stronger now. Very simple with respect to understanding that concept. So guys, what are we doing here? Have a look. I guess this aspect ratio is visible. The process of just one sec. We don't need this video to. All right. The process consists of heating a mixture of raw rubber with sulfur. Now depends on how much sulfur you give. Depending on how much sulfur you give, your rubber will be that much strong. If you give a lot of sulfur, then your rubber would be very, very strong as well. So for tires, the rubber we use a lot of sulfur in there. But for the normal cases, we don't get that much of sulfur. An appropriate additive at the temperature in the range of this to this. Not really remember the need to remember the temperature. Yes, the additive that we give is ZNO. Okay, guys. So this was the vulcanization of rubber. So that's it. This is what I have drawn is. Can you recognize which is the unit? Which is this unit? So pause this video and tell me. Try to answer this. Okay. This is our isoprene unit. And I told you that the isoprene unit, when they get polymerized in the n number of isoprene unit, then what we get is we get the natural rubber. Okay. Natural rubber. Okay. So guys, what you have to do is, now you have to, I am showing you the questions over here. Okay. You can see these questions. Now let's start solving this question. Let's do one thing first. These are the questions that I'm showing you right now. Just watch it and write the answers in the comment section. Okay, I'll be meeting you there. If you get it right, I'll be telling you over there only. This question is very, very important. Okay. And now see the other questions as well. Pause the video and try to write the answers in the chat. I mean, in the comment section. Okay. Then nylon 6 monomer. All right. And then this C PHBV 2019 JMN. Okay. Then try to solve these ones. Okay. So guys, now that would be it. You write the answers in the comment section. I'll be meeting you in there. All right. Bye everyone.